Good evening. Welcome back. We are going to start the fourth technical talk of the workshop. In this session, we are going to introduce the second speaker of the workshop. We are honored to have Professor Sachindeo Vaidya as our speaker. Professor Vaidya is currently working as professor at the Center for High Energy Physics, Indian Institute of Science, Bangalore. Professor Vaidya has completed his MSc in physics from IIT Kanpur and obtained his PhD in physics from Syracuse University, USA. Two postdoctoral degrees, one from TIFR in India and other from UC Davis, California. He has a number of publications in highly reputed journals like Physical Review and European Physical Journal, etc. Professor Vaidya also worked as an associate at ASI CTP Italy and had visiting faculty positions at McGill University Canada and Perimeter Institute Canada. Professor Vaidya has worked in several non-perturbative aspects of quantum field theory like solitons, monopoles, index theory, and spin and statistics. Professor Vaidya also worked on non-commutative and fuzzy physics and recently on matrix models of low energy quantum chromodynamics. Now, before handing over the session to Professor Vaidya, I would like to request Professor Atri Deshmukha to kindly speak a few words. And before that, I request all the participants to kindly turn off your camera and mic. And if you have any questions, kindly put them in chat box. Thank you.
Thank you, Nazneen. So we are having Professor Vaidya with us today, and the titles of his talks, there will be two talks. First one, spin, statistics, and fundamental physics. And then tomorrow he is going to speak on groups, robotics, and non-abelian gauge theories. So I have pasted them in chat box. You can check it from there. And I don't want to waste your time between the speaker and the audience. So I just request Professor Vaidya with lots of thanks from our side for first helping us to organize this workshop. Second, for agreeing to speak on the workshop. So please, session is all yours. Questions will be in the chat box. You can pick them as you wish, maybe later or maybe concurrently with the speak. Okay, over to Professor Vaidya.
Thank you very much, Adri. Can you hear me?
Yes, you are audible.
Oh, okay, great. So I'm very happy to participate and talk in this workshop. Today, what I want to tell you about is about, as my title says, about spin, statistics, and fundamental physics. So I'm going to tell you a little bit about what I mean by spin, what I mean by statistics, and how these two ideas come together to understand some of the very basic fundamentals of physics as we know it. Okay. So I'll start off with a very brief history. And originally, I was planning to give a talk in which I was going to discuss simple applications of group theory to molecular and crystal physics. But I realized that I could combine this into a discussion about spin and statistics itself. So I'll start off with a brief history. Then I will come to a discussion of the statistics of quantum particles, give you the connection between the spin of the particle and the statistics obeyed by many particles, many identical particles of the same type. This connection between spin and statistics goes by one of the most famous theorems in high energy physics. Actually, it's a famous theorem in, I would say, for all of physics, called the spin statistics theorem. Although the proof of the theorem requires us to use a relativistic quantum field theory. So of course, the proof is a little bit technical, so I won't be able to give you the proof itself, but I will be able to give you the ingredients that one requires to prove this theorem. Now, it's all very well to say that spin statistics, that there's a theorem on spin statistics, but as we are physicists, fundamentally our loyalty is to nature, and whether it's a theorem or not, we need to test whether nature agrees with our idea that spin and statistics together form this very nice theorem. So I will describe to you a few tests of the spin statistics theorem, experimental tests, and I'll end with a summary. Okay. Now, in classical mechanics, the idea of identical particles goes back all the way to Aristotle, and then Galileo and Newton. And classically, identical particles have very little interesting to offer us. For example, you might say that particles are identical if they have the same mass and charge and color and size, for instance. But whatever formulation of classical mechanics you use to describe these classical particles, be it Newtonian mechanics or Lagrangian mechanics or Hamiltonian dynamics, the quantities that you are looking at are typically observables. Observables are functions that you create out of positions and momenta. So in particular, if you remember your classical mechanics class, then observables are nothing but functions on phase space. And if you have identical particles, then you require that the observables are invariant under the action of exchange of particle labels. And today I was earlier in the class, Professor Dasgupta talked about the simplest permutation group, S3. So if you had three particles, then the observables for three classically identical particles would be invariant under the action of S3. One of the simplest observables for this would, for example, be the total energy of this particle. So the kinetic energy would be P1 squared by 2m plus P2 squared by 2m plus P3 squared by 2m. And if you had a potential that governs the interaction between these particles, then the potential could be a potential, for example, it could be a pairwise potential. For example, the Coulomb potential, which is like 1 over R1 minus R2 plus 1 over R1 minus R3 plus 1 over R1 R2 minus R3 with, of course, each of the distances, for each of the distances, you have to take the modulus, that's the Coulomb potential, or the gravitational potential. Another potential could be the harmonic potential. For example, it could be R1 minus R2 the whole squared plus R2 minus R3 the whole squared plus R1 minus R3 the whole squared. So these are examples of observables, and if the particles are identical, classically identical, then the potential, the total energy has to be invariant under the action of exchange of any two of the particles. You could have other observables. For example, you could have angular momentum. You could construct many other phase space functions, but the ones that you would call observables would be only the ones that are invariant under the actions of, under the exchange of particles. Of course, the dynamics of this multi-particle system is unaffected by this indistinguishability. And in classical dynamics, classical mechanics, the identity of particles has almost no role to play, no role of any importance to play as far as dynamics is concerned. Now, when you come to quantum mechanics, of course, this is no longer true. And the first serious challenge to this idea that identity of particles is only a footnote, if you like, in the description of its dynamics, came with modern spectroscopy. These are spectroscopic experiments that were performed by Kirchhoff and Bunsen. Now, these you might have in your chemistry used Bunsen burners, but perhaps some of you didn't know that Bunsen was actually a spectroscopist who looked at spectra from various elements in their gaseous form. So this activity started in the middle of the 18th century, middle of the 19th century, around 1850s. And none other than Faraday looked at what happens to the atomic spectrum. But he said, let me put in a magnetic field and see whether there is any effect on the spectrum. At the time that he did the experiment, he found that there was no discernible effect. But it's most probably because he didn't have access to equipment that produced strong magnetic fields. So a few decades later, when Zeeman looked back at this question, he had access to stronger magnetic fields and he had access to better experimental equipment. So in particular, he used these gratings that had been invented by Rowland. And in particular, what Zeeman found is that if you looked at the gas of sodium, then the D lines, the sodium D lines, split when you turn the magnetic field on. And I have a picture for you of the spectrum of the sodium D lines. And the splitting that you see is kind of tiny because the energy of the radiation, the wavelength of the radiation is around 590 nanometers, whereas the split is barely half a nanometer, 0.6 nanometers. But the split, if you like, with hindsight, is the first indication that electrons have spin half. And this point will make a little bit more sense as we go along. But one of the attempts to understand this splitting of the D lines was made by Lorentz. I believe this is the same Lorentz who studied electrodynamics and came up with Lorentz transformation. So you can see that people didn't restrict themselves to just one field. They had interests which spanned several fields. And you can also see that scientists took, theoretical physicists followed experimental developments very, very keenly. This is something that is that's very admirable, and we should try to inculcate it in our own study of physics. But what Lorentz suggested is that if we want to explain this the splitting of D lines, maybe what we should do is we should think of the particle that whose spectrum that we are seeing as a charged particle in a magnetic field, and this might be able to explain the splitting of the D lines very well. But that wasn't really a satisfactory model in the sense that it didn't address the details of what we were seeing. Meanwhile, polarization studies, the cathode ray tube was invented around this time, and the charge of the charge carrier was decided, and by convention it was chosen to be negative. This was, if you like, the beginning of the discovery of the electron. Very soon, Wishart and Kaufman measured the charge to mass ratio, again using the cathode ray tubes. And looking at all the data that had accumulated, Thomson in 1896 proposed this particle called the negatively charged electron. Okay. Of course, by around 1913, the Bohr proposed a model for the hydrogen atom, and it started the quantum revolution. And it led to an intense activity. One of the first things that studied in great detail were atoms. And Pauli, in a series of experiments, in a series of articles over 2 years, 1923 to 25, looked at the Zeeman spectra of alkali atoms and concluded that the stationary states which Bohr's model predicted were labeled by a quantum number J a spin quantum number S, an angular momentum quantum number L, and a total angular momentum quantum number J. And he also found that if the atomic number was even, that is, if the total number of protons of the atom were even in number, then S, the spin, and J, the total angular momentum, were integers. Whereas if Z was odd, then S as well as J were half integers. This half integer threw off people, and it I mean, it was able to explain the data, but it took it was quite surprising. So Pauli said that the doublet structure of the alkali spectra is a result of a classically not describable two-valuedness of quantum theoretical properties of the valence electron. So Pauli is identifying that this two-valuedness of the valence electron has no classical counterpart. So this, if you like, is a phenomenon deep inside the quantum regime that seems to have no classical counterpart. So Kronig suggested that this two-valuedness comes from the may be described, may be interpreted, if you like, from the fact that by saying that the electron has an intrinsic angular momentum with value half. Now, this you realize is somewhat of a revolutionary statement, because if you think of particles, if you think of the classical particles, then they have spins, and of course, if it's a classical particle, then the image that you have of spin is that of a spinning top. Now, you can slow down the top or speed up the top, and you can slow it down by a little bit or speed it up by a little bit. So the angular momentum of the particle doesn't have to have integer discrete values if you thought about this classically. So to assign a discrete value like half to the angular momentum is quite dramatic. And to say that the angular momentum is intrinsic and doesn't really come from classical, from spinning the electron in a classical sense, is actually quite revolutionary. Now, Pauli, of course, when he heard of this idea, said, "Oh, it's a clever idea, but I don't think that that's how nature works." Meanwhile, two other physicists, Uhlenbeck and Goldschmidt, also proposed that the electron has spin half. And subsequently, following the work of Thomas, you might remember Thomas' precession from your atomic and molecular physics class. This idea that the electron has spin half and there is an inherent two-valuedness to the description of the electron gained acceptance. And you can see that Thomas, as I mentioned to you, Thomas also argued that the spinning electron, or to say it better, electron carrying spin half must precess, just like how you expect a spinning particle to precess from classical physics. So this led this body of work that was developing, theoretical work that was developing concurrently with experimental observations, led Pauli to formulate his exclusion principle. So let me briefly describe to you how this happened. The origins of Bohr's work on the periodic table and his permanence principle states that electrons in a shell of an ion keep their quantum number when further electrons are added. There was also the work by Stoner, who argued that if you classify the electrons of atoms by their L and J values, then the total number of electrons is equal to the number of terms in the Zeeman spectrum of the atom. Pauli realized that underlying this classification is a very dramatic principle which can be stated in a rather simple fashion. What Pauli said is that the problem of a more coherent justification of the general rules concerning electrons in an atom here proposed can probably only be attacked successfully after a further deepening of the fundamental principles of quantum theory. So Pauli said that electrons can occupy that if you have more than one electron, then it can occupy only one state, one quantum state. You can't occupy, two electrons cannot occupy the same quantum state. And this was what he called the exclusion principle. The name Pauli exclusion principle, of course, was Dirac who suggested that we name it after Pauli. I don't know if there are any questions because I'm in the full screen mode, and so I cannot see the chat box. But I request Atri to interrupt me and ask, read out the questions from the chat box if there are any. But I think this is a good point for me to stop and ask if people have any questions. Okay, very well. Let me continue. What I want to now describe to you, what I described to you was the emergence of the idea of the spin of a quantum particle. In particular, I only talked about the spin of the electron. But these electrons, of course, were abundantly found. They were easy to create. They were easy to channel in the form of a cathode ray. And they were therefore easy to study. They were the most abundant ones for physicists to play around with. What I want to now tell you about is about the idea about statistics, which is if you have a large number of electrons, if you have a population of electrons, then what kind of properties can we infer about the populations of electrons that are hanging around together in large numbers? Now, the deepening of the theory that Pauli was referring to came with the work of Heisenberg and Born and Schrödinger. And by around 1926 or so, the full quantum theory of angular momentum had been worked out. Pauli principle was reformulated. What it said is that the many electron wave function must be totally antisymmetric under permutations of individual electrons. So if you have a wave function that describes several electrons at the same time, that's a many electron wave function, then if you exchange the particle labels, if you permute the particle labels of individual electrons, say 2 at a time, then the wave function must change by a sign. That is, it must be antisymmetric. So this is how we now understand the Pauli principle, the antisymmetry of a many electron wave function under permutations. A further insight came by the work of Heisenberg and a mathematical framework that was provided by Wigner. And the first application to statistical mechanics of the Pauli exclusion principle as applied to the system of many electrons was provided by Jordan and also Fermi and Dirac. Fowler applied it to the study of a star that collapsed to a white dwarf. Sommerfeld used it to study electronic properties of metals. Fowler and Nordheim studied it to used it to study field emission electron from metals. Meanwhile, none other than Satyendranath Bose tried to understand the properties of particles with integer spin. He was interested in trying to understand what happens when you have a population of photons. Photons, as you know, as we know now, have integer spins. And together with Einstein, he came up. There is a little bit of history behind it, which we can, which maybe many of us know, but I don't want to go into that. But came up together with Einstein. They came up with a principle for understanding the statistics or properties of a collection of photons, which goes by the name of Bose-Einstein statistics. And Einstein went further ahead to predict a new phase of matter called Bose-Einstein condensate, or which is nowadays known as BEC. So if you have bosons, then then Einstein said that in principle, it's possible that that the many particle wave function of bosons can go into a new phase, which he called the Bose-Einstein condensate. And the quantum reformulation of this is that the wave function of many identical bosons must be totally symmetric under the permutations of particle labels. So remember, the wave function of many identical fermions must be totally antisymmetric under permutations. The wave function of many identical bosons must be symmetric under permutations. So I just want to pause and derive some lessons that from these observations. The first point is that quantum mechanics says that the spin of any particle can be only integer or half integer. This was already something, this is a revolutionary statement coming from this new theory that quantum mechanics was. Second point is that under the action of exchanging identical particles, the wave function of the system must be totally antisymmetric or totally symmetric, depending on whether the identical particles are fermions or whether they are bosons. And fermions can have only half integer spin, whereas bosons can have only integer spin. This last statement, that the fermions can have only half integer spin or bosons can have only integer spin, is the connection between spin and statistics. So the spin is about whether it is an integer or half integer, whereas the statistics is about what happens to the wave function under exchange or under permutation of any two of the particle labels. The fact that these two are related, these two get related, is the spin statistics connection. They are no longer independent, but in quantum theory, they are connected. Okay. So let me say this a little bit abstractly. So in quantum mechanics, the permutation group acts on particles. So if I should have written identical particles. But so let me say that out now. The permutation group acts on Sn, acts on identical particles. So today in the afternoon, Professor Dasgupta talked about the permutation group S3. But in general, so the S3 acts on 3 identical particles. But in general, if you have n particles, then permutation group acts on this the space of n particles. Now, of course, as you had in classical mechanics, observables are unchanged under the action of this Sn. In quantum mechanics, of course, the fact that the observables are unchanged under the action of Sn has a rather dramatic effect. So people often describe this as saying that Sn is actually the gauge group for an n particle system. Now, this might seem a little bit confusing because you think that, oh, but isn't it when you apply the action of Sn, doesn't the wave function of a fermion change by a minus sign? Yes, that is true. But remember that the definition of a gauge group comes about by looking at what the group does to the full set of observables. So the idea, the right way to think about this is as follows: collect together all the observables for the system that you have at hand. This, of course, is only a Gedanken, a mental exercise, but collect together. This collection of all observables, with a little bit of thought, you can show, with a little bit of work, you can show forms an algebra. That is, you can compose two observables to get another observable. You can add two observables to get a third observable. So this algebra, this is what you call the algebra of observables. And the algebra of observables commutes with the action of the gauge group. So is left invariant under the action of the gauge group, under the action of Sn, sorry. And any symmetry, any operation that leaves the algebra of observables invariant is, if you like, the definition of a gauge transformation. This is for those of you who are already familiar with some particle physics will recognize that this as the definition of the gauge transformation. Of course, that's not quite the same for wave functions, but wave functions are distinct from the algebra of observables. Wave functions carry a different set of information. They carry information about the state of the system. Wave functions transform according to different unitary irreducible representations of Sn. And today, I think Professor Dasgupta introduced for you these various representations of S3. He talked about the two-dimensional, the three-dimensional, four-dimensional representation, and so on. There are also one-dimensional representations of S3. The amazing thing is that in our 3+1 dimensional world, 3 space and 1 time world, we seem to have only the realization of the trivial representation of Sn, which is appropriate for describing bosons, and the alternating representation, which is again a one-dimensional representation, which is appropriate for describing fermions. In 3+1 dimensions, we have not found any particle which transforms according to any higher dimensional representation of Sn. This is a fundamental experimental observational fact of our world. So to say it in the language of the spin statistics connection, if you have identical particles that carry integer spin, that individually carry integer spin, then they transform according to the trivial representation of Sn. Whereas if you have a collection of identical particles where the individual particle carries a half integer spin, then they transform, then the wave function of this collection transforms according to the one-dimensional alternating representation. In a 2+1 dimensional world, if you have a plane, for example, if you have just x and y, if you have a plane and then you have a time added on, there are more general possibilities. You can have braid statistics, and this I think that Professor Govindrajan will talk about some of these possibilities when he discusses braid statistics in his lectures. Okay. Are there any questions at this point? Okay.
Professor, can I ask a question?
Yeah, please go ahead.
Can you please elaborate the fact about the trivial representation and the alternate representation?
Okay. So let me. If you, I think Professor Dasgupta covered it in his class today, but in case he did not, let me say that. Let me say what a trivial representation is. The trivial representation means that every element of the group is mapped to the number 1. Okay, so S3, if you remember, has 6 elements. 6, right? So every element in a general representation, every element of S3 is mapped to some n by n, is mapped to some matrix. The dimension of that matrix gives you the dimension of the representation. So in particular, if you map elements of S3 to numbers, then we are talking about a one-dimensional representation, because a number is simply a 1-by-1 matrix. And in particular, if you map every element of S3 to the number 1, then you can see that it satisfies the group multiplication laws, and it satisfies the group multiplication laws, and this is called a trivial representation. On the other hand, you can also map S3, the elements of S3, to numbers, but in a slightly more complicated way. Any permutation you map to -1, and then you can get all the other, any other, a general permutation can be obtained by composing the, by composing these elementary permutations. So you see that if you have a cyclic, if you look at the group element corresponding to the cycle 1 going to 2, 2 going to 3, and 3 going to 1, then this one is mapped to identity, as is the identity itself, whereas an exchange of 1 and 2 is mapped to -1, 1 and 3 is mapped to -1, and exchange of 3 and 1 is mapped to -1. So this corresponds to the alternating representation. And again, you can check that this obeys the group properties of the original group that you have in hand, which is S3. I'm sorry, I just want to ask, is there a lot of noise that you hear from my side, or is the audio all right from my side? I'm not.
It's all right.
Okay, let me just close the window. There is some construction work going on in the neighborhood. Okay. Sorry. Does that answer your question about the
Yes, Professor.
representation and the alternating? Sorry?
Yes, sir. It is clear to me now. And
okay.
it is a purely observational fact, right? That the bosons will be a realization of trivial representation.
Absolutely. This is what you get by looking out. This you cannot deduce by sitting with pen and paper and doing computations. This is what you get by doing experiments and by looking out at and by observations. That's right. So there are, of course, many other interesting representations. There are many interesting representations of SN. For example, S3 has an interesting two-dimensional representation, but that is not useful for describing identical particles in 3 plus 1 in a 3 plus 1 space-time. It has other uses, but not useful for describing identical particles in 3 plus 1 dimensional space. When I say not useful, what I mean is that if you make a theory of particles which transforms according to the two-dimensional representation of S3, you will find that it does not describe anything anything in our universe. It may be a consistent theory, but it will not correspond to anything that we see around us. Does that answer your question?
Yes, Professor. Thank you.
Okay. So let me continue. Okay. So as I mentioned, this connection that identical spin-half particles have wave functions that is totally antisymmetric under exchange of any two particle labels, whereas identical integer spin particles have a wave function that is unchanged under the action of exchange of any two particle labels. Is this a theorem? Now, of course, theorems in physics have a very different standing from theorems in mathematics, in the sense that the theorems on physics have to be understood in terms of the hypotheses that go, that we make, the assumptions that we make when we write down when we state that theorem. But to understand this connection a little bit better, what we have seen over the last 100 years or so, since the birth of quantum mechanics since the birth of quantum mechanics about 100 years ago, is that this connection holds in a large variety of physical systems. Of course, in the quantum description of atoms, where it was originally discovered, it has been discovered to correctly hold in describing quantum properties of electrons in metals and insulators and in cold atoms. So when you talk of electrons in metals and insulators, it is the fermionic properties, whereas in cold atoms, you can have atoms that have integer spin, and when you cool down this collection of atoms, you get a Bose-Einstein condensate, exactly as Einstein predicted. These are, of course, non-relativistic systems, but it has been seen to hold in particle physics as well. And in particle physics, we use relativistic quantum field theory because particles can be created or destroyed. Particles travel at speeds comparable to the speed of light, so we can't use non-relativistic methods. So the spin and statistics connection continues to hold away from the domain in which it was originally discovered, which is in non-relativistic physics. It seems to hold, to the best of our knowledge, it seems to hold for quantum particles that are not point particles, but extended objects, like monopoles, solitons, and exotic objects that appear in quantum gravity called geons. And they also seem to obey this connection, that the spin and the statistics are correlated, as was first formulated. So then the question that we need to ask ourselves is this an input that we put in, or can we derive it from a more fundamental viewpoint? So in other words, is it a postulate? Is it something that we put in at the start of the game, or can we derive it from the ingredients that we already have? Now, in non-relativistic quantum mechanics, spin statistics connection is a postulate. It was discovered by looking at a spectra of alkali atoms, and then we decided that it's a good idea for us to impose it on any non-relativistic quantum system that has identical particles. So we put this in as a postulate in any multi-particle discussion, in any discussion of non-relativistic quantum mechanics where we have multiple identical particles. So in non-relativistic quantum mechanics, it's a postulate. So it's not a theorem. You put it in at the start of the game by hand, if you like. Now, if we assume that we can pair create particles, that is, if you allow for the possibility of creating a particle and its antiparticle, then with this assumption, the connection between spin and statistics can be derived. But now you notice that although the connection between spin and statistics can be derived, you now have some other assumption in the game, which is the assumption of pair creation of particles. So you've traded one assumption for the other. For monopoles or solitons, the proof can be supplied using topological methods. And there are studies about what happens for such particle-like extended objects in gravitational, in studies of gravity. There the situation is less clear. But again, there we have no experimental signatures to guide us. But to come back to the question of whether this is a theorem or a postulate, Pauli was first provided us with a proof in 1940. in the context of a relativistic quantum field theory. And his idea for proof uses as hypothesis the following requirements. Okay, that it should be the theory should be a local theory, and as you can see, all these requirements are eminently reasonable and intuitively easy to understand. And we really wouldn't have too much of a quarrel with these as ingredients. So if you start off with a local theory in which all physical particles have positive energy, all physical states of the theory admit a probability interpretation, and all the dynamics that you can impose respects special relativity. In other words, the dynamics is Lorentz invariant. Then, for Pauli, this is enough to prove that spin and statistics are related in the way that we talked about. So Pauli was able to derive the connection between spin and statistics starting from these 4 ingredients. There is a more modern proof, which is technically much more sophisticated, but uses techniques from algebraic quantum field theory that was developed in a series of papers by Doppler, Haag, and Roberts in 3 or 4 years, starting from 69 to 74. So we won't have anything to do with that, but in this talk, I won't have anything to say with that, but I'll try to give you an inkling of how, a sort of a hint of how Pauli went about. So the ingredients of Pauli's proof are as follows. So I have a sort of a cartoon picture here of the light cone. So the hypersurface that I have drawn here, which is, I don't know if you can see my pointer, but I have the origin, which is the red dot, and then I have 2 directions, 2 arrows, which tell you the spatial directions, and then the vertical arrow is the time direction. And then I've drawn for you the cones, which correspond to the propagation of a light ray. So the light ray will propagate along this cone. It can, of course, you can choose its direction. So it can be anywhere on the cone. So this is there are 2 cones here. One is a future light cone and one is a past light cone. So let's consider 2 events that are space-like separated. So let's consider 2 events that are on this hypersurface. So any 2 points on this hypersurface are space-like separated. What locality and special relativity imply is that these 2 events should have no influence on each other. And this should continue to hold even when particles are pair produced. And what Pauli went on to show, it's not very difficult to show, but it requires a little bit of work, is that if you impose these requirements, then if you have fermionic objects, that is, if you have electron-like objects, then the wave function has to be antisymmetric. And if you have photon-like objects, if you have bosonic objects, then these requirements are satisfied only if the wave function is totally symmetric. Okay. Now, the consequences of spin statistics theorem are various, and they appear in a wide variety, in wide spectrum of life, if you like. They appear in atomic structure and in chemistry. For example, if electrons were spinless fermions, that is, their wave function was antisymmetric, but their spin was 0, then we would not have atoms or molecules as we know them. The hydrogen molecule would not exist. There would be no orthohelium. There would be no parahelium. There would be only orthohelium. If electrons were bosons, then the bulk matter would not be thermodynamically stable. It would just keep collapsing and collapsing and collapsing, and matter would exist only as extremely super dense clumps. So each one of these tells us the important consequences of this spin statistics theorem. The periodic table, if you like, is a very important consequence of the spin statistics theorem. In fact, the early work, one of the early successes of quantum theory was a very beautiful and logical explanation of the periodic table. So that was, of course, from atomic physics. But you can also look deeper. You can look at shorter distance length scales and look at the atomic nucleus. For example, if you looked at the nucleus of the lithium atom, then it has its atomic mass is 7. It has 3 protons and 4 neutrons. Now it's well known that a free neutron is unstable. If you take a neutron and if it's not part of a proton, if it's not part of a nucleus, then it decays under weak interactions. The lifetime of the neutron is about 1,000 seconds, I think. But on the other hand, if it's part of the nucleus, then the neutron does not decay. Inside the nucleus, for example, inside the lithium nucleus, the neutron cannot decay because I should have said this earlier. When the neutron decays, it decays into a proton, an electron, and an antineutrino. But inside the lithium nucleus, it can't decay because the accessible proton states are already occupied by the 3 protons. And if you were to decay, then it would require you would have to give it much higher energy for it to occupy a proton state, a much more a highly excited proton state. So in other words, you would have to bombard the lithium nucleus with and give it sufficient energy to for the neutron to decay. But then you're not surprised, because if you're bombarding the lithium nucleus, then all bets are off the table. But a stable lithium nucleus, in a stable lithium nucleus, the neutron will stay as it is. And the simplest way to explain its stability is because of the Pauli exclusion principle. Now, of course, as physicists, when a principle like this is proposed, we must try to push this principle to its extreme. We must look for exceptions to see if there are exceptions, we must look for limitations. So over the last 50, 60, 70 years, physicists have tried very hard to see if there are violations of Pauli exclusion principle. We've searched very hard. There is a famous experiment called the Borexino experiment with carbon. The latest data is from about 10, 11 years ago. And what they do there is to look at a carbon nucleus and try to look for Pauli forbidden transitions, like a transition from a C12 to an excited C tilde 12, which is an extra nucleon in the 1s half shell. And what they have found is that if at all such a decay occurs, then within the limits of the experimental apparatus that they have, the branching ratio for such a decay is less than 10 to the power minus 25. So this is, if you like, an experimental limit, one experimental limit on the Pauli exclusion principle. There have been others. There's a beautiful result coming from the work of Landau and Yang, and this comes in the context of a relativistic theory. What Landau and Yang independently showed is that if you have a massive spin 1 particle, then there is absolutely no way that it can decay into 2 photons. Okay. For example, in the standard model, you have the Z boson, and it's a massive spin 1 particle. The Z boson decays, but it cannot decay into 2 photons. So the idea is and this work of Landau and Yang comes again from this result of Landau and Yang comes from looking at essentially looking at the bosonic version of the exclusion principle, although I shouldn't really use the word exclusion in this case, although it might be in some very restricted sense. We might be allowed to use the word exclusion because it tells us that a spin 1 cannot decay into 2 photons. But again, it comes from identity from the identical nature of the decay products. The 2 photons are identical, and what Landau and Yang independently showed is that such a process cannot take place just by looking at the kinematics. Okay, so in the standard model, for example, we can look at the branching ratio for Z going to gamma gamma. And unfortunately, the detection process is very complicated, and the constraints from Z going to gamma gamma are quite poor. There have been other experiments. There's an experiment from about 20 years ago where they search for a 2 photon transition in atomic barium. And again, they find that the violation of the spin statistics connection, if at all, is less than 1 in 10 to the minus 7. So again, these are branching ratios. Okay. So this is a test of spin statistics for bosonic particles. The earlier one that I described was for fermions. But if we see these violations, if at all we see these violations, what will these violations teach us? What exactly will we learn if at all violations of spin statistics are discovered? What it means is that one or more of the following will have to be abandoned: locality, Lorentz symmetry, or the probabilistic interpretation of quantum mechanics, of quantum theory. Because these, if you remember, were the basic ingredients of Pauli's proof that if you have a local relativistic quantum field theory, then spin and statistics are necessarily correlated in the form of the spin statistics theorem. So if we do find in nature, in some corner of nature, either at extremely high energies or at very, very short distances, if we find violations of the spin statistics theorem, then one or more of these basic building blocks that went into Pauli's theorem will have to be abandoned. That means that nature in that corner where you see this violation is either not local or violates Lorentz symmetry, or more dramatically, cannot be incorporated into quantum mechanics. All this would be very exciting, of course, because it would signal new physics and therefore require us to search for more fundamental principles, because if these principles have to be given up, then there must be a more fundamental, then as physicists, we hope that there is a more fundamental way of organizing the behavior of nature in that corner. Okay. I want to just point out that there have been such attempts, and one such interesting consequence, one such interesting violation of the correlation between spin and statistics has been proposed in a class of theories called non-commutative theories. So in order to build up to that, I want to point out a very interesting consequence of the standard spin statistics theorem, which is that if you have two identical fermions and you scatter them, then the scattering amplitude vanishes at 90 degrees. So if you take 2 electrons or 2 protons and you scatter them, then the scattering amplitude is 0 at 90 degrees scattering. This vanishing of the scattering amplitude is actually independent of the interaction. So it doesn't matter whether these particles interact via electromagnetism, or it doesn't matter if they interact via strong interactions or via weak interactions. If the particles are identical fermions, then the scattering amplitude vanishes at 90 degrees. So, for example, if you take 2 identical fermions, and if you find that if you postulate, or if you work in a theory in which the scattering at 90 degrees is non-zero, then this would indicate a violation of the spin statistics theorem. So many years ago, with AP Balachandran, whom you heard yesterday, Babar Qureshi, Sasha Pinzul, and myself, we discussed a particular version of non-commutative quantum field theory, where we showed that very, very close to Planck's scale, you would find such violations of spin and statistics. And there, of course, the reason why why this so you might go back, you might ask, which of Pauli's 3 fundamental ingredients did you violate? And it turns out that we violate both locality and Lorentz symmetry. So Lorentz symmetry is violated in this particular version of the theory. In locality, it's locality that is violated, not Lorentz symmetry. In this particular theory, and that's why you see a deviation from the prediction of the spin statistics theorem. Of course, this deviation occurs only when you do extreme high energy scattering. So if the electrons scatter, if you scatter 2 identical fermions in this theory at very low energies, then you will not even be able to pick up the difference. It will be within the observational bounds. Okay. So I'd like to, looks like I'm finishing before time, but I'd like to summarize the spin statistics theorem, if you like. What the theorem tells us is that particles with half integer spin have to be fermionic, and those with integer spin have to be bosonic. And by fermionic, what we mean is that if you take the multi-particle wave function and exchange any 2 particle labels, then the wave function is antisymmetric. By bosonic, what we mean is that if you take the multi-particle wave function and exchange any 2 particle labels, then the wave function is invariant. The Pauli exclusion principle, which is the fermionic version of the spin statistics theorem, it explains a wide variety of phenomena, starting from the stability of atoms and molecules to the formation of white dwarfs and neutron stars. In fact, some of you may know that Chandrasekhar's work on the collapse of a star to form a neutron star relies crucially on the Pauli exclusion principle. And the collapse, according to Chandrasekhar, occurs when the gravitational attraction is so strong that it overcomes the effective repulsion produced by Pauli exclusion principle. Now, the proof of this exclusion principle requires us to have locality, Lorentz invariance, and positivity of energy. That is, the state that describes any physical particle has to have positive energy, and these are the conceptual ingredients. And despite the existence of a proof, the proof is not simple. Its complexity suggests that one should look for deeper and fundamental explanations. We should also keep looking for experimental as well as conceptual challenges to the spin statistics theorem, because it is through these challenges that we hope to find new physics, and we hope to that key model independent windows will open to new fundamental physics. So this, if you like, is the connection between spin, statistics, and fundamental physics. It is through challenges to the spin statistics theorem that we can hope to discover new fundamental physics. Thank you. I will take questions now if you have any.
Professor?
Yes.
Is there any connection between every Lorentz symmetric theory should satisfy CPT invariance?
Yes.
Is it somehow connected to spin statistics theorem?
No. The fact that any relativistic local quantum field theory obeys CPT is a different theorem. In fact, it is as you pointed out, it is a theorem, and it's a different theorem. Theorem different from the spin statistics theorem of relativistic. They are independent theorems.
Okay. And I had another question. Can I ask?
Yes. Yes, of course.
In the proof that Pauli gave,
Yes.
he claimed locality and positive energy.
Yes.
Then can I say he excluded the fact of antiparticles in his proof? Because if they are locally, I mean, they can affect phi x at one point and phi y. Their commutator should not be zero. I mean, observation at one point can affect observation at another point. So I excluded the fact of especially not connected. But if I included the fact of antiparticle, then fact of causality could happen or something like that. Did he exclude the antiparticle?
No. Antiparticles are, in fact, relative. If you are familiar with quantum field theories, then you know that relativistic quantum field theory has built into it antiparticles, right? So,
yes.
So it is in fact a part of his starting point. They are very much a part of his game to start with, and he doesn't have to introduce antiparticles by hand. They are present in a relativistic quantum field theory, and in fact they are important, if you like, for the proof to go through, because if there were no antiparticles, then the proof wouldn't work.
Okay, then what's the meaning of spatially separated regions you talked about?
So, spatially,
there should be coherent causality effect. I mean, their commutator should be
spatially
zero,
separated
but
means that
propagator particle can travel through one point to another that are spatially separated, right?
By by space like separated, what I mean is that if you take the space-time coordinate of one particle and space-time coordinate of the other particle and compute their Minkowski distance.
Yes, x minus y square whole square is less than 0.
Then they are called spatially separated.
Spatially separated.
Yes. So, for example, in this picture that I have drawn, if you have a particle, if you have two events that lie on the on the plane that I have drawn. Any 2 points on the plane that I have drawn obey this condition that you just mentioned.
Yes.
Okay. If you Pauli's proof starts off by looking at two events that are spatially separated, and then goes on to look at what happens to the two particle state, with one of them localized at x and the other localized at y. The two particle state where one particle is localized at x and the other particle is localized at y, where x and y are space-like separated. And then he shows that, then he makes his argument. So as I said, the proof is not very difficult, but I cannot, I mean, it will take me away from, it would have taken me away from what I wanted to show you, that the requirements of causality, locality, and special relativity are satisfied only if the two particle state has is antisymmetric if the two particles are identical fermions, and is symmetric if the two particles are identical bosons.
Okay. Thank you.
Okay, sure. Okay. Any other question? I can see that there is one question. Neeraj Kumar has asked, what does it mean by a theory being local or non-local, mathematically and physically? So, locality means that, like I said, locality is fundamental, if you like, in what we call locality makes sense only in the context of special relativity. So local means that space-like separated events do not influence each other. So in any theory which respects special relativity, this is what you demand of this. This is what you demand, and if this demand is met, then such a theory is called local. You can have, of course, interactions. You can make up a theory that has interactions in which the interactions depend on points that are space-like separated. Such a theory would not be local. This is both, if you like, the mathematical as well as a physical description of what it means, what a theory means, what it means to be local or non-local. If you think about it, non-relativistic quantum mechanics is a non-local theory. And this, you might have not thought about it in this way, but one way to see this is that if you take the wave function of a particle that is strictly localized, in other words, a wave function of a particle which is localized at, let us say, the origin of your space, and let's say it's a free particle, and then you make an evolution by an infinitesimal amount of time, you find that the wave function has spread over the whole space, right? You must have done this exercise in your quantum mechanics class. And this means that the propagation, the propagation in, I'm sorry, not propagation, time evolution in non-relativistic quantum mechanics allows for the particle which was initially localized at the origin to be found anywhere else in your space. So this, if you like, is an example of a very important and very useful theory, which is at its heart, at its core, a non-local theory. And this because in non-relativistic quantum mechanics, the speed of propagation, if you like, is infinite. There is no limit at which signals can propagate, right? So this is an example of a theory which is very useful, very important, but also fundamentally non-local. There is one more question. Shivatosh Bishwas asks, why are we interested in finding the violation as because of the complexity of explaining the theorem? Not so much of the complexity of explaining the theorem, but because the theorem seems to be so dominant, if you like. Everything that we see around us is consistent with the theorem. So, anything that you find, which if you find a phenomenon, if you observe something which violates the spin statistics theorem, it will be very, very exciting, right? Because it would tell us that the basic building blocks of modern physics, locality, causality, special relativity, and positivity of physical states, one or more of them needs to undergo a drastic and dramatic revision. This will require us to revolutionize physics as we understand it. If you like, the kind of thing that we are looking for is the closest analog I can think of is that the speed with which any particle travels, the maximum speed is finite. Now, if you were doing only low energy experiments, then you would see that a particle can go faster and faster and faster, and therefore hypothesize that therefore the particle, if I had enough time and money and energy, then I could make the particle travel at whatever speed I like, no constraint. But it was Einstein who pointed out through a series of brilliant arguments that is actually not possible. The maximum speed that a particle can travel is constrained by the speed at which photons travel, or by the speed at which gravitons travel. Einstein didn't talk about gravitons, he talked about photons, and in particular, he only talked about light. So, so tomorrow, if we found that there were particles that traveled faster than the speed of light, it would overturn physics as we know it. And some of you may know that some years ago there was excitement because people in an experiment, joint experiment between CERN and a laboratory in Italy, people thought that they had discovered neutrinos that traveled faster than the speed of light. It was both exciting and disturbing because it would have overturned entire physics as we know it, entire particle physics, entire relativistic physics as we know it. Subsequently, when people read the experiment much more carefully, they found that no, those neutrinos don't travel faster than the speed of light. In fact, there was the experimental error was allegedly because of a cable that was loose and had introduced a phase lag or a time delay, which then got interpreted as neutrinos traveling faster than the speed of light. I just brought up these couple of examples, speed of light, as well as this neutrinos, as something that we keep looking. Although we know that, although we know about special relativity, we keep looking for phenomena where we challenge this, because physics is not mathematics in the sense that there are no theorems. You discover new things in physics by discovering phenomena that do not fit into your current set of explanations. So this is the reason, if you like, why we are constantly interested and we maintain a deep interest in looking for violations of the spin statistics theorem. I hope that answers your question. There is one more question by Nilotpal Bhattacharji, who asked what is the meaning of positivity. I guess his question is in this context, all physical particles have positive energy. So it means that another way to say it is a more colloquial way of saying it is that the Hamiltonian of your system, the Hamiltonian is a positive operator. You may allow for negative energies, but the negative energies should be bounded from below. So the Hamiltonian that we have should be bounded from below, because then you can always redefine the zero of your energy so that all the energies are positive. So all physical particles or all physical states should have positive energy. This is what we mean when I say positivity. Okay, there's another question by Athar Ahmed. He asks, is the concept of particle and antiparticle actually acceptable in Bose-Einstein statistics? Now, the concept of particle and antiparticle is something that you require in the proof of spin statistics theorem. So this is something that you require when you are proving it using a paper and a pencil. You don't, for experimental realizations, you don't actually need antiparticles, right? Experimentally, what you need is simply a bunch of bosons who you cool sufficiently so that they collect together and into a nice big clump, if you like, and whose wave function now acquires macroscopic dimensions, and this macroscopic wave function is described as a Bose-Einstein condensate. So for Bose-Einstein statistics, for Bose-Einstein condensates, you don't need a particle-antiparticle. But I think maybe I misunderstood your question. Your question was, why do you need particle and antiparticle to discuss Bose-Einstein statistics? To discuss the statistics itself, you don't need particles and antiparticles, because what statistics tells you is that if you have a multi-particle wave function of identical bosons, then the wave function is unchanged or invariant under the action of the permutation of any two particle labels. This is a statement about statistics. If you want to connect it to the spin of the individual particles, that make up your collection, if you want to relate it to that, then you need then you are talking about the connection between spin and statistics. So again, experimentally, there is such a connection, and to prove, if you like, that there is a connection, to prove the theorem, you need particles and antiparticles. I hope that answers your question. Okay, is there any other question? I'm sorry, I think that is someone trying to speak?
I think what they're trying to speak. No, he has put off his microphone again. So okay. I don't think there is any more question. Any participant wants to put in question? Questions are already answered. I mean, whatever was asked.
Okay.
Yeah. So I think we can stop for today.
Okay. So thank you very much, and thank you for your questions.
Yeah. So they can always get back to you. Finally, I will
Absolutely.
Give anyone wants, they will get your contact with your permission
Absolutely,
if
no
it is
problem.
there. So we will see to it afterwards. But right now we may stop and have a half an hour break, and we assemble back here at 6 o'clock.
Okay.
So I thank you, Professor Vaidya, for this nice talk on spin statistics. It's nice. It was really nice, the concept-wise, as you have put it. So thank you once again. We come back here at 6 o'clock, and we are stopping here for today. I mean, not
Okay.
today, this session only.
Okay.
Yeah.
I'm going to stop the presentation.